Hello, everyone. My name is Angela Zabaleta. My pronouns are she and her. I am a second-year PhD student at the University of Toronto working at the Intelligent Adaptive Interventions Lab. I'm going to talk about using adaptive experiments to rapidly help students. When we run embedded experiments, how can we analyze data using machine learning or artificial intelligence algorithms to more rapidly give a better intervention to future students? Specifically, we focus on multi-arm bandit algorithms, a fundamental form of reinforcement. You can access the slides at tiny.cc aaaiontrack. What is a randomized AV experiment, and how can we combine them with machine learning or artificial intelligence algorithms to accelerate the speed with which we discover what works for students and use that data to improve the experience for future students? Randomized AV experiments, also known as randomized controlled trials, uniformly assigns user to various arms that we might want to explore to learn about their relative effectiveness. As we want to improve the experiences that students get with technology, we deployed a real-world experiment in an introduction to programming class. We sent the students weekly email reminders about the homework with a direct link to the exercises to encourage them to start those early. As we designed multiple variations of these emails, we used A/B tests to see which version was better. So which version got students' attention and encouraged them to click on the homework link. As we get the data, how do we enhance the experience for future students? More generally, how do we run adaptive experiments in the real world? To do that, we want to use machine learning or artificial intelligence to use the data and constantly improve our intervention. A multi-arm bandit problem, one of the most fundamental forms of reinforcement learning, comprises a set of arms or actions, each of which has an unknown reward or value. From our previous example, the different emails can be arms, and the rewards whether people click on the embedded homework links or not. The goal is to assign arms and use the data to maximize the reward over a period of time, the quality of the arms people get. We use the multi-arm bandit algorithm Thompson sampling to use data to rapidly assign more people to the current most effective arm that we're testing. The algorithm will continually update the probability of assignment to an arm to be proportional to the likelihood that an arm is effective. To give a concrete example, we might want to start with a uniform distribution of 50-50. The distribution may change to 40-60 or 20-80 based on the data, as more evidence accumulates that the second option is better. However, there is a second goal that's less commonly emphasized. Scientists want to do statistical analysis of data from experiments to draw conclusions about whether or not an effect exists. It's problematic to have a false positive conclude from a statistical test that differences exist when they don't. But we also want to have high statistical power, the probability that when a difference in arm exists, we detect it. To both help students more quickly and gain scientific knowledge from experiments, we need an algorithm and statistical test that trade off between reward and statistical analysis, as measured through properties like false positive rate and statistical power of a statistical test conducted on data from adaptive experiments. You can see our manuscripts on archive or on request, characterizing the statistical issues, as well as proposing algorithms for better managing the trade-off. In this presentation, we show some real-world adaptive experiments that inform some of the issues and provide novel settings and data sets for machine learning, artificial intelligence, and applied statistics researchers to explore adaptive experimentations. So we're trying to identify what is the range of real-world experiments that we should be applying these algorithms to. The bandit algorithm can increase how many people get the better arm as there's an effect observed. So in cases where there's an observed effect, this works well. But in cases where there is no effect, as will show, the bandit algorithm, by its adaptive nature, can cause issues in a statistical analysis, as adaptation can lead to unreliable inference about which arm is better. One can see a clear case where bandit algorithms gives better arm more often. Let's look at the simulation we ran with 10 million observations. Coming back to our setting of email reminders, consider this scenario with 4 email versions, where after the first batch, we found that the reward of arm 1 is 20% and 10% for the other arms. As we go along, more and more students will get assigned to arm 1. Even with a small difference, we saw a large effect. Now, this was a simulation. Real world data is not always as pretty. We are going to go through some interesting experimental designs that we have been exploring. Here in this deployment, there seems non-stationary. We have 4 arms and 4 batches that happen within the same week. We apply bandits here, but it raises some questions such as, are there differences or not? Is it stationary or not? In this work, we use the Thompson sampling multi-arm bandit algorithm when a difference between arms is not clearly observed. So the arms are equally or very similarly effective, according to the traditional uniform random experiment. Fortunately, while Thompson sampling may randomly favor an arm, this has no negative consequences on the participants, so they would not be assigned to a suboptimal arm. As part of a follow-up and ongoing study, we're now measuring email engagement with email open rates for 13 consecutive weeks. We again explore the impact of using an adaptive multi-arm bandit algorithm, but now to assign students to 3 versions of subject lines. This algorithm learns from the prior week's results, potentially leading to more students being assigned to the more effective subject lines. For the first 4 weeks of the experiment, we assigned each subject line uniformly. In week 5, we split the students into 2 policies, a uniform random assignment and a standard Thompson sampling assignment, similar to what we did in our previous study. The Thompson sampling policy would get all the cumulative priors from the uniform data collected in previous weeks to learn which arm is performing the best. In the following week, we compare the standard Thompson sampling algorithm with one that learns from a combination of data that was collected using Thompson sampling algorithm and data collected uniformly during prior weeks. To be able to balance the power, we only pass half of the priors from the standard Thompson sampling and uniform data. We repeated this process for the rest of the weeks of the deployments. This may mean that fewer students are assigned to the best performing arm in a single week, as not all students are assigned adaptively, but may yield benefits for these same students in later weeks by allowing the algorithm to react more quickly to the changes in effectiveness. Our question now is if including some randomness in our Thompson sampling algorithm allows it to react to non-stationarity more directly. The results for this work are still in progress of being analyzed, so if this work is of interest to you, stay tuned for the results. When we apply bandit algorithms like Thompson sampling to real-world adaptive experiments, we see the trade-offs in reward and statistical analysis, such as false positive rate and power. In our first case study, we show how bandit algorithms can increase misleading false positive when arms are equally effective. In our second case study, we illustrate the opportunity for better managing non-stationarity in sequences of adaptive experiments, potentially by adding more uniform random exploration into the traditional Thompson sampling. We hope the case studies mentioned today highlight important considerations for future work on using bandit algorithms in the real world, such as drawing statistical inferences from data in adaptive experiments. Thank you for listening, and we will be happy to chat more about our work and take more questions later. And again, you can access our slides at tiny.cc /aaaiontrack and visit our lab's website to learn more about our current projects.